Thank you very much to you, to the organizers for this invitation. Okay, so I'm going to talk about non-Newtonian fluids. So let me write down just first of all what are the equations I'm dealing with. So these are the following equation. So we have incompressibility condition, divergence of U equals 0, and then the momentum equation, so dtu plus u grad u, so the material derivative. Then there is a pressure here. And so here on the left-hand side, we do not have the Laplacian, so it's in the Navier-Stokes equation, but we have something else, so the divergence of a different shear stress tensor. Let me write it in T dot of du, where, so what are these objects? So where this T dot of du is the following function, so it's a function nu of the modulus of the u times du. So this is this du is the symmetric gradient, so grad u plus grad u transpose divided by 2, and this function nu is the following function, mu0, which is a constant, plus mu1 times du to the power q minus 2, and then there is this du. Okay, and this q is a number in the range between 1 and infinity. Okay, so this is, let me call this system NN, so non-Newtonian. So this is the system of equations that I'm going to deal with. Let me just observe from the very beginning that this, okay, mu0 and u1 are constant, maybe. Okay, I write it here. mu0 and u1 are constant, bigger or equal than 0. They can also be 0. So let me just observe from the very beginning that if q is equal to 2, then this is just a constant, so we get back the Navier-Stokes equations. But somehow we want to consider this generalized fluid. And okay, so first of all, let me give you like some sort of motivations why one wants to study this kind of equations. And I will give two types of motivation, like mathematical ones and more physical ones, hopefully. So let's say motivations. First of all, so from the point of view of math, this kind of system, well, with a slightly different choice for this shear stress tensor, in particular for this function nu, was proposed by Ladyzhenskaya in her 1966 talk at the ICM as a sort of let's say, so relaxation of the Navier-Stokes equation. So in the sense that Navier-Stokes equations are difficult, so we want to study something easier in some sense. And at least for q bigger than 2, this kind of model can be seen, as we shall see later, as a sort of relaxation of the Navier-Stokes equation. And so let's say relaxation of the Navier-Stokes equations. And at the same time, this is not just a choice for this shear stress tensor, but it's a choice which is somehow coherent or consistent with the first principle of continuum mechanics. And so consistent with principles of continuum mechanics. For instance, in particular with the frame indifference principle. So it's not just an arbitrary choice. On the other side, so there are also, let's say, more physical motivations in the sense that there are physical systems which are modeled by this kind of equations. Let me make the following observations. So from the point of view of physics and also engineering applications, you see that so we have a whole range of shear stress tensor depending on this parameter q. We have already observed that if q is equal to 2, then we have a Navier-Stokes equation with viscosity constant equally 1, but I can put another viscosity here, just another constant. So let's say for q equal 2, we have the Navier-Stokes equations, which means that so the shear stress tensor, so some of the friction between different layers of the fluid, is directly proportional to the velocity gradients. Now, what we are doing here with this choice of nu is somehow to allow our fluid for having a viscosity which depends on the velocity gradients. And you see that there are, in particular, two big classes. The class when q is bigger than 2, okay? And in this case, this function nu, so the function from du into nu of du, which is just a real value function of real variables, is increasing. Whereas in the case q less than 2, this is a decreasing function. And so somehow the kind of modeling we are doing here, we are saying we want to model fluids for which the viscosity is not just a constant independent of everything, just a property of the fluid, but it can change with the velocity gradients. And in particular, we can have cases where the viscosity increases when the velocity gradients increases, and cases in which it decreases when the velocity gradients increases. Just to make a common life example, for instance, if you take for the case q less than 2, so when the viscosity becomes smaller when you have a high velocity gradient, so the ketchup that you put on French fries is such example. So it's quite a viscous fluid, but if you shake a bottle of ketchup, then it becomes less viscous. So if you increase this velocity gradient, then the viscosity somehow decreases. And there are also examples clearly for q bigger than 2. For instance, a quite funny material, it's called oobleck. And I mean, I didn't know the existence of this material. So if you are like bored with this talk, if it's too boring, you can Google this and you find plenty of movie. It's a sort, so it's a liquid material with, I mean, quite liquid. So if I just put this chalk, then it would fall down in the liquid. But somehow if I throw the chalk in the liquid, it doesn't fall down immediately because I am putting like a large velocity gradients, and the fluid becomes much more viscous, much more solid-like. So if I do like that, then it stays on the top for some short time, and then it starts going down. Okay, good. Okay, so but now let's go. So this was just to say, okay, these are somehow like funny examples, but you can imagine that this kind of materials can have plenty of applications in the industry. Okay, so it's interesting to study this kind of model. Okay, so far so good, but let's say what we want to do is clearly to do some analysis. And so let's see. Yes, so to start doing some analysis, let me observe that as for the Navier-Stokes equation, we have a total energy associated to the system. So you take your equation, you multiply scalar product with u, integrate by parts, the usual procedure, and you get that there is a total energy. Let me write it down. This is clearly 1/2 of the kinetic energy. Okay, and then there is a dissipative term, which in this case, for this kind of system, is the integral from 0 to t in time, the integral in space, and then we have this non-constant viscosity times the modulus of the velocity gradient squared. Okay, so you see, if nu is constant, it's the Navier-Stokes energy. Otherwise, we have this other kind of energy. Let me say that I am considering this system in a general dimension. So let's say bigger or equal than 2, even though the result I'm going to present holds for dimension bigger or equal than 3. So let me just write here d bigger or equal than 3. And as a domain, I will take the periodic torus, just so periodic boundary conditions. Okay. Okay, so fine. So we have this total energy, and now somehow the first thing I want to do is to find a good notion of solution that I want to use. And okay, I will introduce 3 different notions of solutions. Let me give the following definition. Okay, so the first one is the notion of distributional solution, which everybody knows, but what's important is which integrability we need to define this notion. So a distributional solution, let's say a distributional solution is a map U in, okay, we need clearly, so L2 lock integrability, let me write it like that, L2 lock in time and space, to make sense of the quadratic term. And then, okay, what kind of integrability do we need for this shear stress tensor? So you see that this viscosity is behaving like du to the q minus 2. Then there is an additional du. So this one is behaving essentially like du to the q minus 1. So we need this gradient, this symmetric gradient, but let me just put the gradient in Lq minus 1 lock of time and space. So distributional solution is a map U with those integrabilities solving the equation my non-Newtonian system in the sense of distributions. Okay, so this is somehow the weakest, a very weak notion of solution. Now, let's improve, let's upgrade a little bit this notion of solution. I said we have an energy, so we could look for solutions which fall in the energy class. So for solutions for which this energy is well defined. And this is, okay, my second definition. So this was distributional solution. And now I have what is an energy, I will call an energy solution. And this is a map U, is a distributional solution. Distributional solution U, for which in addition this energy makes sense. So let me write so such that this U belongs to L infinity in time, L2 in space. And so you see that once again, this viscosity is Q minus 2. And here I have an additional 2. So to make sense of this term, I need the gradient to be in LQ, not in LQ minus 1. So one more integrability. So is a distributional solution U for which which stays in L infinity L2 and for which the gradient is in LQ of time and space and not locally anymore because here I have the total integral, so globally in LQ. Okay, and then last notion of solution I introduced, so we upgrade it a little bit more. So this is just a distributional solution inside the energy class, and now we can look for Ladyzhenskaya solutions as for Navier-Stokes. So this is the third notion. So a Ladyzhenskaya solution is an energy solution for which let's say E is decreasing. So the total energy is decreasing. Exactly as for Navier-Stokes. Okay, so these are some of the three notions of solution that I'm going to use. And okay, yes. And so what I want to do now is, so before presenting like our contribution to the theory, so our application of convex integration to this system, let me very briefly summarize what is the state of the art, so what is known about existence and uniqueness of solutions for this kind of system. And I will just very briefly do that in the sense that I will unfortunately not mention many people who work on that. So this is, so what I will present now, the state of the art is like the end point of a very long story, many results. I'm not going to mention all of them. I will just give a very brief overview. So what is the state of the art? Okay. So there are essentially two exponents which play a crucial role in this business for this equation. One is, so let's say two critical exponents. So one is the what I will call the compactness exponent. And this compactness exponent is essentially the exponent for which the space W1Q embeds compactly into L2. Okay, so W1Q embeds into L2 compactly if so Q is less than, what's that? It's 2D divided by D plus 2, where D is the dimension. Okay, so this is what I will call the compact. Sorry, for Q bigger than that. Okay, this is what I will call the compactness exponent. And you can imagine that if I have a Q which is larger than this, I can use some compactness method to produce a Ladyzhenskaya solution. And in fact, this is what happens. So in this case, what has been proven is the existence of Ladyzhenskaya solutions. Let me put this maybe, I don't know, maybe here, like let me do a short picture. So this is my Q. So here I have 1, here I have 2, here I have 3, and all the other Qs. And this 2D divided by D plus 2 is somewhere here. For instance, in 3 dimension, this is a 6/5. And so this result I will put like something like this. So here we have existence of Ladyzhenskaya solutions. Okay. as I said, so this is not just a single paper, it's really a long story, but due mainly to the Czech community, the Prague community, essentially. Okay, second interesting exponent is what I will call the scaling exponent. So the equation has a scaling, which is, so as a natural scaling, u of xt mapped into, what is that, lambda to the alpha, u, so then here we need alpha plus 1, t, maybe let me put t and x, lambda plus 1 t and lambda x, and this alpha is something like q minus 1 divided by 3 minus q. Now, something like that should be this. So there is a scaling you can compute. And now, so what is the scaling exponent? The scaling exponent is the exponent for which LQ, so L2, so the kinetic energy space, L2 is subcritical with respect to this scaling. Okay, so L2 subcritical with respect to the scaling. And this happened if this Q is bigger than this plus 1. So 2d divided by d plus 2 plus 1, which is 3d plus 2 divided by d plus 2. Okay. So take the, for instance, in dimension 3, this is 11/5. Okay. So for Q bigger than that, L2 is subcritical. And then you can expect that in this subcritical regime, you have not only existence, but you have uniqueness of solution. So you have well-posedness of the theorem. In fact, this is what has been proven. So this is uniqueness of solutions, of, let's say, Clairaut solutions. Let me put that. So this scaling exponent is always between 2 and 3. That's somewhere here. 3d plus 2 divided by d plus 2. And let me put like that. So here we have uniqueness of Clairaut solutions. Actually, uniqueness really of energy solution, according to my definition.
Yes. So Q has to be larger, spherical larger, not equal. For the uniqueness.
It could be, I don't know, it could be equal, yes.
Probably, yes.
Yes. Yes. Okay, let me put bigger equal. Thank you. Okay, so this is somehow the, let's say, the state of the art. Then, so the theorem I'm going to state now is a sort of dual picture to what we have here. Okay, let me state it like in a sort of statement, sort of theorem. Let's see. I can write here. Okay. Yes, I can. Okay. Good. So this is the theorem that we have proven. Okay. So as I said, in dimension d bigger or equal than 3 and periodic boundary condition, the theorem has, so actually it's 3 theorems, it's 3 statements, but I will just state them in a single theorem. So the first one is that, so if we are below the scaling exponent, so this 3d plus 2 divided by d plus 2, so for q less than 3d plus 2 divided by d plus 2, we have proven essentially non-uniqueness of distributional solution. I don't have the definition. Okay, non-uniqueness of distributional, so just solution in the sense of distributions. So we have proven that essentially there exist u and v distinct, so they are continuous from 0 infinity with values in L2. They are different and they have the same initial datum, which is achieved strongly because this is a continuous up to time 0. And they have also some better, so also the gradient has some integrability, some continuity in some LQ minus 1 space. But let me just write that. So we have 2 solutions which are distinct and we have the initial datum. So essentially we have non-uniqueness of distributional solution. There exists u and v, different same initial datum, u and v distributional solutions. And actually, so the way we achieve this theorem is somehow the usual convex integration business, in the sense that what we can prove is much more. So not that just that there exist two, but there exist infinitely many of them. There exist infinitely many data for which this holds, and so on. So we have a sort of, so what we can prescribe, so prescribed kinetic, we can prescribe the kinetic energy. So we can prescribe the part, the kinetic part of the total energy. Okay, given a profile, we can produce a solution with that energy profile, and this gives us a corollary, this non-uniqueness. Okay, so in this picture, this means that if we are here, essentially, so here we have non-uniqueness of distributional solutions. Okay, so you see, in particular, in the case, so the case Q equal 2, which is Navier-Stokes, is included in this statement, and this is indeed what Tristan and Vlad proved for the Navier-Stokes equation. And in fact, also somehow the proof that we have for this theorem is very much inspired to what they did for the Navier-Stokes equation. So in some sense, we sort of, well, let's say generalized in some sense, but so we generalized that proof to this, so to this non-Newtonian system, essentially. Okay, so this is the first part of the statement. Then second statement is that something better if we are below the compactness exponent. So if Q is less than this 2d divided by d plus 2, we have the same statement. So non-uniqueness, essentially, same statement as 1, but with U and V Ladyzhenskaya solutions. So we can prove non-uniqueness really of Ladyzhenskaya solutions, of solutions having, so let's say, decreasing total energy. Okay, and in fact, what we can do here is we can prescribe the total energy, not just the kinetic part of the energy, but really also the dissipative part of the energy. Given a profile, we can construct a solution such that the total energy is exactly the given profile. It's a prescribed total energy. Okay. And finally, okay, let me put that in the picture also. So the statement is essentially that if we are below this compactness exponent, so if we are here, we have a non-uniqueness of Ladyzhenskaya solutions. This is the statement. And essentially in this regime, you see that nothing was known. So there was not even an existence result. Okay. So, and again, so this is a non-uniqueness where the initial datum is achieved strongly in L2. Okay, as in the point 1. And then finally, we have a third part, which is actually an existence statement. So again, in the regime when we are below the scaling exponent, so this 3d plus 2 divided by d plus 2, so when we are here, what we can prove is that for any initial datum in, let's say, L2, divergence free, there exists a map U, which is continuous on the open time interval with values in L2, which is converging weakly in L2 to the initial datum, and which is a distributional solution to the equation. So we can prove essentially for any initial datum in L2 existence of a distributional solution, which is not really interesting in this regime between compactness and scaling exponent, because here we already have the existence of Ladyzhenskaya, but here below nothing was known. So this is sort of something. Okay, so we have existence of distributional solutions here. Okay. This is some of the picture. So this is the statement that we have. Okay.
2 imply 3 here, or is that different?
No, it doesn't imply, because here this is just for some initial data. You cannot do that for every initial data because, okay, so let's say the point is the continuity at time 0. Okay, so for some initial data, you can construct these infinitely many solutions starting strongly from that initial data. What we have here, also here, we have infinitely many solutions, so it's also a non-uniqueness statement, but the initial datum is achieved in this weak sense. So there is a jump in the energy essentially at time 0.
I had another silly question. The scaling here, it doesn't mean that the equations are invariant under scaling, right?
Yes, sir.
Oh, it does.
It does. That's the yeah. Sorry.
Okay.
So if U solves the equation, also the Riscade solve the equation.
I see. Okay, I was just like a bit concerned because that guy is not constant.
There is new and new, not and new.
Yeah. Okay. Right. No. Okay. You are right.
Okay. Okay. Fine. So it just
I forget what I said. My last sentence. You are right.
okay. Okay.
So what is a critical exponent for the weak strong uniqueness here?
For the weak strong uniqueness.
What?
Good question.
I would say that also 11/5, right?
In dimension 3.
Yes. So 2D over D plus 2, right? As well.
So yeah, 3D
plus 2.
This one.
Plus. For weak strong uniqueness. No, starting from 2D plus 2 over D plus 2, you have basically regularity problem, right? I mean, that's already that's a good regime when you have just everything. Weak strong uniqueness should start earlier, probably.
Yeah, weak strong uniqueness might start earlier. Yes, I agree.
I would
Should
say
start. Should start.
Yeah, it should start earlier for sure.
It should start early. Yes. Yes. But I don't know.
So it's not 2D over D plus 2, right?
I'm not aware of like of a result, so like of a proof of that. But okay. 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 Okay, good. So what I would like to do now is okay. In the last,
in principle, it might even be below, right? I mean, like for Euler, there is weak strong uniqueness without any viscosity.
okay. Yes.
So it could be even below. Yeah.
Yes.
Well, okay. So when I say so when I say weak strong uniqueness in the array sense, so basically any smooth solution is unique in the class of Hopf solutions. All right. That's what I mean by weak strong.
Okay.
That's true even for Euler.
Yes. Yeah.
Okay.
Yeah.
That could start.
It might be true everywhere in this case.
Yeah.
But you need one solution, which is in the uniqueness.
Right. Right.
Yeah, you're starting from a strong solution. Yes.
Right.
I mean,
So
you're assuming that.
Yes. Okay. Thank you. So what I would like to do now in the remaining half an hour. So it's so not really a proof of the results because it wouldn't make sense. But I want somehow to convince you that these two exponents which pop out here are sort of. So first of all, I want to convince you that they are sort of necessary conditions in the sense that if we can do convex integration, we must be below these exponents, okay? And then that they are also sufficient in the sense that we can indeed do that, okay? But let's start like to see where they pop out, so where they come from. Let me erase something. Maybe the first record, maybe. Yes. Okay. Yes, okay. I had this remark maybe that there are really, so we checked somehow in the literature, in the physical engineer literature, there are really models in 3 dimensions. So in 3 dimensions, this is a 6/5, and there are really model which uses Q smaller than 6/5 in 3 dimensions. So and here we have really non-uniqueness of Hopf solution, so the correct notion of solution, if you want. So it's not just, I mean, it has some meaning also from like that the model is, I don't know, it's not readable, I don't know. Okay, so where do these exponents come from? So where do the conditions on Q come from? Okay, so to do that, to answer this question, I need briefly to recall, and it was luckily done already on Monday by Ladyzhenskaya, but let me do that once again to briefly recall how this convex integration business works. So we want to construct a solution to the equation U, and the idea is that, so this is non-unique solution with prescribed energy, okay, I don't care. So we want to construct a solution, and we want to do that so to construct it as a limit of a sequence of approximations, UQ, where this Q goes to infinity. So Q is a natural number going to infinity. And this UQ is an approximate solution to the equation, not an exact one. So which means that this UQ satisfies essentially what? dt UQ plus divergence of UQ tensor UQ plus gradient of, okay, some associated pressure, PQ. Then we have minus, in our case, the divergence of this T dot of DUQ, our shear stress tensor, non-Newtonian shear stress tensor. And here we don't have zero, but we have an error, which one typically writes in the form the divergence of some RQ, some Reynolds stress, so some error. And then clearly the incompressibility condition. And the idea is that this RQ has to go to zero, so in some norm as Q goes to infinity. And in particular, the norm that we are going to use is the L1 norm in space. Well, L infinity in time, but it's important, so L1 in space. Okay, so this goes to zero, so it means that this goes weakly to zero, so in the end we have a weak solution to our equation. Okay, so some of the main task is then, given UQ with some error, construct UQ plus 1 with a much smaller error. So this is some of the main tasks. So given UQ, construct UQ plus 1 with the new error, RQ plus 1 in our norm, much smaller than the previous error. Now, how do you do that? Well, you do the following ansatz. You say, I define UQ plus 1 as UQ plus a perturbation that let's call WQ plus 1. And the goal, so that the aim of this perturbation is exactly to somehow to reduce the error, to cancel the error. Now, if I assume this ansatz, and let's compute what is the equation satisfied by UQ plus 1. So I write dt UQ plus 1 plus the divergence of UQ plus 1 tensor UQ plus 1 plus the gradient of PQ plus 1. Well, I should also define what is PQ plus 1, but let's focus on the velocity field. Then we have minus divergence of T dot of the UQ plus 1 equal. So this will be my new error. And now one does the computation, one plug in this ansatz. And after some computation, you see that, so essentially when I apply this operator, this differential operator to UQ, I get my old error. So I will get a term of the form divergence of minus RQ. Then when I apply this divergence of the product to W, I get a term of the form WQ plus 1 tensor WQ plus 1. And I put them together inside the same divergence. And then, okay, then there is a term coming from this tensor field. So there is a term of the form divergence of T dot of DUQ plus 1 minus T dot of DUQ. And then there are other terms which I'm not going to write today. Okay, one has to take care of them, but today we forget them. Okay, so somehow we have these two main terms, and let me observe. So what one has to do is one has to design this W so that both. So you see, I want to write the error as the divergence of something. Here I have the divergence of this one and the divergence of that. So I want to design W so that both this and this becomes much smaller than the previous error. This is my goal. And okay, let me write it here. And the first line of the error, this W tensor W minus R, is exactly the same error that Camillo and Laszlo had in the framework of the Euler equation, essentially for proving the Onsager's conjecture. And then in addition, we have this new term, which appeared also in, so this new term, which for Navier-Stokes equation appeared also in the paper of Tristan and Vlad, of course. So let's see. So we want, first of all, as I said, this first line, so WQ plus 1 minus WQ plus 1 minus RQ in, let's say, L1 to be much smaller than the old error RQ. This is the first requirement. So we want a W such that this, roughly speaking, holds. And then the second requirement is that we want as well a W for which also the second line is small. So this DTUQ plus 1, maybe let me put it slightly below. So T dot of DUQ plus 1 minus T dot of DUQ in L1 is again much smaller than the previous error. And now, okay, what can we deduce from these two inequalities? From the first one, this is a tensor product. So from the first one, we deduce that if this has to be much smaller than this, it has to be very small. So it means that this W tensor W has to be essentially of the same order as R. And this is the first condition that we get here. So we get that W tensor W, let's say RQ in L1 has to be of the same order as W tensor W in L1. And well, W squared in L1 is W in L2 squared. So from this first condition, so we need to be able to design a W perturbation for which the L2 norm of W has to be of the same order as the L1 norm of the old error. This is the first requirement. And then we have the second. What can we deduce from the second? Well, let's say, so this T is my, so let me recall what was T. Let me put it here, because I think it's not anymore. So this T du was my mu0 plus mu1 du to the q minus 2 times du. So it's clearly non-linear, but let's say that it behaves like a linear function. So this means that this difference has to be approximately T of the difference of these two guys, which is exactly D of WQ plus 1. And now what is at least the growth of this T dot? Well, we have a Q minus 2 and then an additional 1, so it's Q minus 1. So roughly speaking, this part of the error behaves like the modulus of D W Q minus 1 to the power Q minus 1. And we want to take the L1 norm of that. So we want a W for which the L1 norm of this is much smaller than RQ, and the L1 norm of this to the Q minus 1 is just so my D Q minus 1 derivative in L Q minus 1 to the Q minus 1. Okay, so from this heuristic, one can see that, so I need a perturbation W for which the gradient in IQ minus 1 is much smaller than the old error, which is of the same order as W in L2 itself. And this is possible only if W1 Q minus 1 does not embed into L2. Otherwise, it's not possible. This is possible only if W1 Q minus 1 does not embed into L2. And this happens if Q minus 1 is less than 2D divided by D plus 2, which means Q less than this plus 1. So exactly Q less than my scaling exponent. And that's why, so this is where this scaling exponent comes from in our setting. So why we can do it. Okay, and this one comes from, I mean, so if you want to construct an array of solutions, then you need somehow to treat also the kinetic, so the dissipative part of the total energy, which stays in W1Q. And so you need the W1Q to fail to embed into L2. And so you get the other exponent. Okay, so this is in some sense where this exponent comes from. And now let me try to give at least an idea. So why? So this is why they are sort of necessary. Let me try to give you some idea why they are also sufficient for this construction. And okay. Okay, so the point is how can we choose? So how to choose this WQ plus 1? This is the question. And once again, let's look back at these two. So we want to somehow to make small these two quantities. And this I was mentioning, this is the quantity that appeared also already in Camillo's and Laszlo's work on the Euler equations. And so the first step I want to do is like to recall how one can make small this quantity 1 by using essentially the tools of the Euler equation. So make I small. This will be my first step. And the second step I want to discuss is how, so to achieve also this point 2, we need this Sobolev embedding to fail. So the second point is how do we find an example? So how can we prove that this Sobolev embedding fail? Okay, which is just a trivial exercise for every undergraduate student, but maybe I will say something. So failure of Sobolev embedding. And then the third point is how can we somehow combine point 1 and point 2 to construct a W which makes this first part of the error small, and at the same time somehow we can see in this W a failure of the Sobolev embedding. So combine 1 and 2. Okay, so, and once again, I would like to stress once again that so this proof that we have is very much inspired to what Tristan and Vlad did for the Navier-Stokes equation. We have a sort of different approach in the sense that, for instance, we do not use Fourier analysis, we just do that in the physical space. But I mean, so I want to to say it very, very, so so it's very much inspired. Okay. Okay, so how do we make this first point small? Well, so what was Camillo's and Laszlo idea for the Euler equation? So point 1, the idea was to define this W, Q plus 1 of T and X as some phase function A, let's say AQ plus 1 of Tx, times some capital W, which is a sort of given building block which does not depend on Q, and it is fast oscillating lambda Q plus 1 X, where this lambda Q plus 1 is a very large natural number. And this W is just a given building block which has to satisfy some properties. And what are these properties? Well, we want, at least they wanted in the Euler case, they wanted to construct a solution to the Euler equations. So it's natural to somehow to require to construct a building block which is a solution to the Euler equation. It does not depend on time, so it has to be like a stationary solution. So the properties that we want, so properties on this WQ plus 1 that we want, it's first of all that it is, let's say, divergence free, that it is, well, maybe with a pressure equal to 0. And then, okay, then there is a third property, which says that essentially this W has to be non-trivial. Otherwise, one could just pick 0, but of course, 0 doesn't help very much in cancelling an error. And this non-triviality condition is expressed in the fact that this sort of quadratic form, W tensor W in mean value, has to be equal to psi tensor psi, where psi is a given vector, is a given unitary vector. So for any given psi, one should be able to construct a profile W for which these three conditions holds. And why are these three conditions important? Okay, it has to be a solution because we are constructing a solution. Why is this important? Well, because you see, if I look back at that first line over there, so the guy who should cancel the old error is this W tensor W. So if I compute here what is W tensor W, this WQ plus 1 tensor WQ plus 1, this is what? It's A is A squared times W fast oscillating tensor W. Okay. And now, so if I take the mean value of this W tensor W, and I take lambda sufficiently large, this is somehow the dominating term. So what I get is essentially A squared times psi tensor psi. So the idea is that at least on some length scale, this W tensor W has this form. And this is the typical form of an error RQ, actually. So one can decompose the error RQ into a sum of guys of this type, and then one uses, for each term in this sum, one uses one of these building blocks. Okay, somehow this is a sort of motivation why we want that. But what's important is that we want these three conditions, and how can we achieve them? Well, there have been proposed in the literature essentially two different building blocks. One are the Beltrami flows, so-called the Beltrami flow, and the other one are the so-called Mikado flows. Let me present what are the Mikado. This Mikado flow, introduced by Laszlo and Sara some years ago, we have said for every psi we need a W satisfying these three equations. Let me just pick, let me just say in dimension 2, and let me pick psi equal to E2. So what I define, so I take a function phi, periodic, and such that its mean value squared is equal to 1, and it does not depend on the second coordinates. And then you define W of x1, x2, just as phi of x1, it does not depend on x2, times E2. And now it's clear that this is divergence free. It is a solution to Euler even without pressure. And it has this property of the mean value, just because phi squared has mean value 1. And somehow the picture, that one is here, and maybe I will do the picture here, because I'm going to use it. Okay, so what is the picture that we do have? Essentially, so we have this function phi, which depends just on x1. So it's essentially, let's say that it has compact support, it's essentially a pipe. And let me put here also another pipe pointing in the opposite direction. I mean, it's just a matter of the choice of phi. And this is my direction E2, so this is essentially what a Mikado flow is. Okay. Yes.
But the viscous term is too large for Mikado flows. They don't even work for.
Sorry, can you say it again?
Mikado flows don't even work on the Stokes. The viscous term is too large.
Yeah, sure. Now I'm going. This was just. Yes, this was just. Let's say that this point 1, which was somewhere. So. Yes, so I removed it. Okay, so it was just how we can get rid of this first line. Okay, now, as you said, it comes the second line. How do we do that? Okay, and this has to do, as we have seen, with the failure of the Sobolev embedding. So, okay, so failure of the Sobolev embedding, failure of Sobolev. For instance, how do you show that W1Q minus 1 does not embed in L2 when you are below this exponent? You take, for instance, a function, let's say psi of compact support on Rd, and then you define psi mu of x as mu to the power d over 2 times psi of mu x, where this mu is a very large number. And then what you have is that the L2 norm of all these functions is essentially 1, but so if you take a derivative and you compute what is well, the derivative of this psi mu in LQ minus 1, you have mu to the d over 2, then there is a plus 1 coming from the derivative, and then we are computing the LQ minus 1 norm. So there is a d over q minus 1. And you see that this exponent over there is negative exactly when q is below this scaling exponent. So we have a family of functions for which the L2 norm is 1, but the gradient in LQ minus 1 goes to 0. So the Sobolev embedding cannot hold exactly in this range. Okay, fine. So what do we do now? Now we have to combine that Mikado with the failure of the Sobolev embedding. And so we need, for instance, a Mikado with compact support. Okay, so what do we do? Okay, so one could try, first of all, to make like we remove a part of the Mikado here, and we make it compactly supported. Maybe it's better if I rewrite here what are the conditions that we want on this Mikado. So divergence free, 0 acceleration, and mean value of W tensor W equal to, in my example, E2 tensor E2. Okay. Now, if I do that, I can still keep this property, but of course I lose completely divergence free and I lose completely this 0 acceleration. So what do we do? Let's see. So you can imagine that maybe let me remove a little bit more. Okay. So how can I recover, for instance, the divergence free condition? Well, I can imagine that I put like here a small piece tube joining this, okay, where the fluid is going like that. Now this is divergence free. Okay, but of course, what's the problem if I do that? The problem is that I lose, so one of the, forget this for the moment, one problem is that I lose this mean value property because now I have added also horizontal component to my fluid. And what do I do to recover that? So I do the following. So I needed to introduce first some, let's say, yes. So I do the following. Let me introduce something. So let's say when I have a single Mikado like that, the length of this tube is essentially something of order 1. And this also this length is something of order 1. I mean, I don't know, it's 1/4 of that. I don't know, something of order 1. Fine. I have divergence free. I don't have this. I don't have that. What do? I do the following. Let's do it here. So instead of having just a single Mikado, I pick a very large natural number, mu, and I put many of them. Okay, so I put many Mikado here, one pointing up, the other pointing down with their small part which joins. Then I have another one, and so on. So. And so on, like new of them. They are divergence free. Now, what are the length scales which are involved here? So this is a length scale, again, still of order 1, but this length scale has become of order nu, of order 1/nu. Okay, if I have nu of them. And what's important is that also this length scale, so how big this junction should be, is also of order 1/nu. Okay, so let me compute now what is this mean value. So what is the mean value of W tensor W? So let's compute first the mean value of the vertical parts. Okay, the vertical parts gives me a contribution E2 tensor E2, and then what is the area? So the area is I have essentially n tubes, and each, so I have, sorry, nu tubes, and each tube has an area which is 1 times 1/nu. So 1/nu. So this is the contribution given by the vertical tubes. And now let's see what is the contribution given by these junction parts. So will give me something like, let's say, E2 tensor, E1 tensor E1. Let's say that here is really horizontal, just for simplicity. How many of them I have? I have nu of them, again. I have nu of them. but what is the area of each one of them? Well, once I put nu of them, the area is 1 over nu times 1 over nu. So it's 1 over nu squared. Okay. And now you see this gives that here the nu somehow cancels, and here I have still a 1 over nu. So I have E2 tensor E2 times 1 plus 1 over nu E1 tensor E1. And now if nu is large enough, essentially I can get rid of this, at least approximately. I have back this condition on the mean value that I want. Okay. Fine, so we have the first condition, we have the third condition, but still we don't have the acceleration equals 0. So what do we do? Let me go back to this picture. Let me remove now, just forget this part. It's there, but I don't want to have in the picture because there is already too much in this picture. Okay, so I have just this. And now, so what's the idea? Let's see. Oof, I have 3 minutes. So, okay. Fine. So first of all, what is this acceleration? So if I compute what is this W times gradient W in this picture. So here, essentially, what I have here, this, let's say, W tensor W here is a vector pointing down here, pointing down here, pointing up here, and pointing up here. And it's a vector of order 1, essentially. Okay, it's not small, it's order 1. Okay, now, is that small in some sense? Because, okay, maybe 0 is too much, but is that small? Well, it's not small. It's for sure not small in any strong norm, because it's order 1. Is it small in some weak sense? Okay, what does it mean, weak sense? It means that it has to be essentially, let's say, on cubes of order, I don't know, 1 over nu. The mean value of this W gradient W is equal to 0. If I can find like a sort of partition into very small cubes such that on each one of these cubes the mean value is equal to 0, then I would have something weakly small, roughly speaking. But this is not possible here because it's true that the mean value of these green vectors is 0 over the whole torus, so over a cube of order 1, but not over smaller cubes. Okay, so what do I do? And so, okay, and here the idea is the following. So the idea is to let this Mikado move. So I have my W and I define U of Tx as W of x minus omega T E2. So I let this Mikado move in time. And what happens now? Okay, I don't have to look anymore to this stationary or acceleration, but I have also a part which is a dynamical acceleration, dtw, let's say dtu, let me write it here. So I have to consider now dtu plus u scalar gradient u equals 0, or at least approximately 0. Okay, so this part, this statical acceleration is always the same, is my green vector. Now what is dtu? If this omega is very large, so dtu here is a very large vector of order omega, and dtu there is a very large vector by pointing down again of order omega. So the total acceleration is somehow here omega minus 1 pointing up, and here it's omega plus 1 pointing down. And now what happens, just, okay, then I conclude. So what happens is that this total acceleration, so this dtu plus u gradient u, now is not anymore 2 vectors of the same order, but it's 2 very large vectors, which looks very much similar, okay? One is omega minus 1, and the other one is omega plus 1. But somehow if I look, if I take like this circle and I ask what is the mean value here, the mean value is still of order 1, is still 2, but somehow these 2 vectors looks very much, so I mean, they are very large, so a difference of 1 is not really important. And concretely, how is that done? Well, it's done by making this vector here slightly longer, of order 1 plus 1 over omega, and this one slightly shorter. But okay, unfortunately now the time is over, so I will stop here. I hope at least to have given some ideas. Question?
So the Lorentz solutions that you construct, do they satisfy energy inequality?
Yes, so they are really Lyarev.
It means there is no strong uniqueness in that region because it's not compatible with convex integration.
No. It starts from a bad initial data, though.
Yes.
So you don't have a smooth solution.
No, but if you have a bit strong uniqueness, automatically you have Lyarev structures in it. And so basically,
no. I mean, you have weak strong uniqueness for Euler, and there's no Lyarev structure.
but no, I mean the one I'm talking about uniqueness of smooth solutions in the class of Lyarev solutions, right?
And you have it for Euler. In the class of solutions which have decreasing energy, if you have a smooth solution in that class with a smooth initial data, that's unique. Even though you don't have regularization effect.
But for Navier-Stokes, you automatically get Lyarev structure theorem from this, right? Because your initial data is almost
because you don't have epochs of regularity.
Oh, because in that
because you don't have epochs of regularity.
So
you need enough regularity.
Okay. So in that region,
I would imagine so.
So basically, you don't have a local existence of regular solutions, right? Basically,
well, you have local existence of regular solutions, but when you start from a non-smooth initial data, you don't have almost everywhere in time regularity of these guys. I mean, like the regularity, the estimate that you have, right? It's not strong enough to show.
Not strong enough for. Oh, I see.
Yes.
Okay.
Because I mean, the integral, you're not integrating gradient of u squared anymore, but you're integrating something which is just small.
Okay.
So like the trace is not in the supercritical for almost every time, so that you can get that's the issue.
Oh, I see. Okay.
So what's the regularity in LQ you get of the solution? Then you just have distributional solutions and not Lyarev.
So you mean so this kind of like distributional solutions?
I mean, more in the next region. Yeah. What's the regularity you have?
For the solution or for the derivative?
For the derivative. I mean,
the regularity.
LQ.
Yeah. So it's the derivative is in LQ minus 1.
No, but I mean, if you measure in LQ, what's the derivative? What's the Sobolev space if you measure in LQ? Because that's
okay. So the partial regularity you mean, not the partial regularity. I mean the fractional regularity that you have. I mean, you can do the computation. I think I don't have an answer in mind, but we can do the computation.
Okay, sure. But I mean, for Lyarev, it's 1, right? You have one full derivative in L.
In LQ, yes.
But then suddenly, does it drop close to 0, or does it interpolate nicely?
I think it does interpolate nicely.
So even in the Navier-Stokes case where Q is 2, you have some regularity which is much better than H beta, where beta is small.
Well, we have W16/5, but in H alpha spaces, we have very small alpha.
So here, I guess the analog is in LQ spaces, you'll always have very small alpha. Is it always going to be W alpha 2? Alpha is very small. Okay.
Yes.
And so there's a sudden jump there. You have 1 just before, and then you just jump down to very small alpha.
Yes. Okay.
I see.
So you give us heuristics why it's somehow 3d plus 2 divided by d plus 2 is optimal for the distributional solution.
Mm-hmm.
But in principle, at the level of the Lyarev solution, there could still be an overlap, right? Between, I mean, you could think that you can still use convex integration to go a little bit further, right? You don't have a reason to believe that is okay. I mean, for instance, one reason could be the epochs of regularity. So you have to be below that threshold.
Right, definitely.
Do you know what that threshold is actually over here? Have you computed? When you would be able to apply, say,
partial regularity.
Yeah, like Lyarev does, right?
Yeah.
So it should be a little bit more than this d 2d divided by d plus 2, because that is just a compactness threshold. So it's like
yes.
I just had one more. Do you have anything in 2 dimensions, or d equals 2, or?
Well, no. So in the sense that for d equal 2, I mean, let's say that if you just take Euler, you can apply this kind. It's not really interesting because you get, I mean, L2 solutions of Euler, but in that case, d equal 2 will be okay. But as far as you put this non-zero shear stress tensor, you need at least dimension 3. Because otherwise you don't have, essentially, you always need to be below this compactness exponent a little bit to control the dissipative part.
And that's one.
And that's one.
No, you can construct distributional solutions which are not unique.
Yes, but in dimension 3. So in the sense that you need this exponent still to be bigger than 1, strictly bigger than 1. Otherwise, you do not control the dissipative part. In dimension 2 plus epsilon, yes.
So I'm still confused. I'm sorry. So there's no that region where you said non-uniqueness of distributional solution. The next region,
right? This one
that doesn't exist in dimension 2.
No, it doesn't exist in dimension 2. You're right. So this exponent is strictly bigger than 1 in dimension 2, but still for the proof you need also this one to be strictly bigger than 1.
I see. Okay.
Yes.
So in principle, there might be some other.
Yes.
There might be some other way of doing it.
Yes, sure.
So what breaks down in the proof again? Can you explain?
So let's see. So it depends. Let's say, for instance, the problem is that you have this dissipative part, and you need to control it, and somehow, so you need to control that part in L1. Okay, so let's say that you are in dimension 2. Okay, this one is exactly 2. Okay, so you are here, but what can you do? You need to control this du. Okay, what is that? Du to the power q minus 1. Okay, and if let's say if you are in dimension 2, this is exactly 2. Okay, so q minus 1 will be for sure smaller than 1. Okay, because I mean, so if q is smaller than 3d plus 2 divided by d plus 2 in dimension d equal 2, this is 2. Okay, so somehow this statement in dimension 2 would be that you have a tensor field for which q is smaller than 2. So q minus 1 is smaller than 1. Okay, and then it means that since it's smaller than 1, the only way we have to control it is to control L1 norm. But if you are in dimension 2, you cannot control L1 norm of the derivative and at the same time so you cannot have this small in L1 and you order 1 in L2. That's the point in the proof.
Not necessarily, because if you just look at the building block itself, you can deal with norms, L2 norms for q less than 1, right? Why not? I mean, it's basically just have the same scaling. Right? You can just compute it directly, right? You can just I mean, it's a simple building block.
But yes, you mean you could measure the error in.
Why are you giving away q minus 1? I mean, that power is over there, so and that integral makes sense.
Right.
But it tells you that you have to use a norm actually.
You don't need to use
so you mean that you could use like
try to compute that guy.
But that you measure the error in this norm essentially.
Yeah, in the L1 norm of that, guy, which is the true error. I mean,
yes, you could. Right.
Principle.
I mean,
yes, in principle, yes.
Okay. Any other questions?
Yes.
Let's thank the speaker.
Thank you.